We're supposed to start the quiz at around 3:30. Maybe we can start it a little bit later. It shouldn't take most of you that long to do, a half an hour. So let's go ahead and get started then. So I want to talk about topographic mapping. So topographic mapping all boils down to the law of cosines. You'll be very happy to know. So it's very, very simple and it's interpretation. So what I'm going to do is I'm going to have two observations separated by the baseline. So that's going to be a baseline length of V and an angle with respect to the horizontal of alpha. I'm going to make my two observations. So I'm going to have a range rho and a range rho plus delta rho from my second antenna. Now the interferometric phase is going to give me something that's proportional to delta rho. And notice the 2 pi here, so this would be the single antenna transmit version. If there were 4, it would be the ping pong type configuration. So from the law of cosines, we can get that sine of theta minus alpha is related to the range and to the baseline length. So where does that come from? So the triangle I'm looking at is this one. Here, here, and here. And so what do I know? I know from the law of cosines that rho plus delta rho squared will be equal to b squared plus rho squared times the cosine of this angle here. Now, this angle here is alpha. This angle here is going to be what?
90 minus alpha.
Right, pi over 2 minus theta.
Yeah.
So if I have cosine of alpha plus pi over 2 minus theta, that turns into a sine. That's where the sine came from the law of cosines. And then if I solve the law of cosines algebraically, I end up with this formula. Okay, that's all fine and good, but how does that help me? Well, suppose I wanted to know the height z here of the ground topography. And I know, because I have a good GPS say on my airborne platform, I know how high I would fly h. Well, again, by using right triangle trigonometry, if I draw a line straight over to here, the length from here to here is going to be what? In terms of rho and theta. I draw a line straight across here.
Rho sine theta.
Almost, what's the other possibility?
H minus.
Well, I'm only looking at I want to know the distance from here to here. Draw a line over from Z to here, and I want to know what this distance
Oh,
is.
that's rho cosine.
Rho cosine theta. So H minus rho cosine theta, that will be Z. All right, so what don't I know? I don't know theta. Well, how can I get theta? Go back up to this equation right here. I can solve from theta from this equation here. If I know what the baseline length is and the baseline angle is, I will now know what theta is. And I have to know what delta rho is, but I get delta rho from my interferometric phase. So the phase gives me this delta rho. Baseline, I'm assuming I'm measuring V and alpha, and then from that I can get to theta, and then I get the topography. So it all boils down to the law of cosines and knowing the interferometric phase. How many people here have taken a surveying course? Civil engineering. There's a couple people here. All right. Well, for those of you who come from the civil engineering community, you're going, you guys are absolutely crazy. This is the wrong triangle for trying to solve for anything. Well, why is that? Because this is a long, skinny triangle. And if you've done surveying, you know that long, skinny triangles are the worst thing in the world for doing surveying because it's so sensitive. You get lots of gigantic errors when you're trying to do that. So why are we trying to figure out this angle when I have a stupid, long, skinny triangle? What allows me to get away with that? The way I get away with that, the why reason interferometry works is because I know this distance so accurately. I can measure this to millimeter scale. So even though I have a very long, skinny triangle, I know this so well that I'm able to get away with that. But it also puts very stringent demands, extremely stringent demands on knowing the baseline length and the baseline angle. So there's nothing's for free. So my penalty for being able to use this is to be able to know what the baseline is. And then I can use interferometry and I can determine the elevation using this. So that's the basic idea of measuring topography with interferometry. Are there any questions? Now, that's the two-dimensional version. In the real world, we have to do it in 3 dimensions. And I'm going to skip all of this stuff because although it's very interesting to me, we don't have the time for it to go through it. But I will mention that the interferometric phase is the projection of the baseline onto the line of sight. And if we write it in terms of those angles that I had previously, it's b times theta minus alpha is that distance right here. The direction of the baseline perpendicular to the line of sight, or the length perpendicular to the line, that's called the perpendicular component of the baseline. And the baseline length along the line of sight is called the parallel component. You'll see, particularly oftentimes in the literature, that people will be met for seeing the perpendicular baseline because that's the sensitivity of the phase. So, some of your quiz problems might involve this too as well. Just remember, the perpendicular component is the length perpendicular to the line of sight. And there's the formula for the parallel component right there. In the perpendicular component, you replace the sine by a cosine. And the p, remember I told you, could be 1 or 2. That's how I tell the difference for the 4 pi and the 2 pi case. So and this equals here is really a misnomer. This is an approximation. This is the real formula. That is an equals. And this is an approximation down here. This is just another way of doing that. Now, how fast do the fringes change? So this is something that we do care about. So how fast do the fringes change in range, and how fast do the fringes change in azimuth? So this is called the fringe frequency and the azimuth fringe frequency. And there's a big difference between the two of them, which I will mention in just a second. So the range fringe frequency depends upon the perpendicular baseline length. The bigger the perpendicular base, the faster the fringes change. So as I make that perpendicular baseline length longer, I'm going to get faster and faster fringes. It's inversely proportional to the wavelength and the range. And it depends upon the local slope. And again, notice that theta minus the cross-track slope here. And the tangent of 0 is what? 0. So dividing by 0 is a no. So, because you get infinity. So remember, so you're going to get really fast fringes on slopes facing toward the radar. And in fact, if you're looking in the same direction, the slope is equal to the look angle, your perpendicular, then you have infinitely fast fringes. So that is not good. So this is how fast the fringes change in range. Notice what happens, even if phi sub c equals to 0, this derivative does not equal 0. So even over a flat Earth, the fringes change, okay? So I always get cross-track fringing because this formula here says if that's non-zero, then I'm going to be changing the fringe rate across range. What happens in the azimuth direction? In the azimuth direction, I have the same sensitivity to the wavelength, the perpendicular baseline, and the range. But this time, the fringes depend upon times the tangent of the along track slope. So the slope of the terrain in the along track direction. So in this case, if there is no slope in the along track direction, the tangent is equal to 0, and there is no fringes. So in the azimuth direction, I have to have a slope in order for there to be for the fringes to be changing along track. But in the cross track direction, they do not. So this leads to a process that people talk about, which I don't know if it's on the next slide or not. But yes, the flattened phase. So people often do not want the fringes over a flat Earth to change. They only want to see fringes if there's actual topography. And to do that, we do what's called flattening, and that's basically we remove the fringes to a flat local surface. So we pick a reference surface, a flat surface, or a curved Earth surface for a sphere or ellipsoid, whatever we want, and then we subtract that off, and then we're left with the fringes, and these fringes will then depend on having a cross-track slope. So you have to be careful when you're looking at fringes in an interferogram. You need to understand if they've been flattened or not, and if they've been flattened to what reference surface in order to be able to interpret them properly. A lot of people show their fringes, like the fringes I was showing off earlier. For most of the scenes, they were flattened already. But sometimes people don't do that, so you just need to be careful to understand what has been done to the data. Another way of writing the flattened fringe, you can do it in terms of using that angle that I had here for delta theta. This delta theta is related to the height of the terrain and basically the range and this angle here. So that's going to be rho sine theta. So delta theta is HT divided by that. And so you can write this flattened phase in terms of the height of the terrain. So you can see the varying elevations affect the flattened fringes. So the flattened fringes reflect the local topography, which is what you often want to have happen. And that's what you can see from that formula there. This is an example of mapping on the moon. This was done from an Earth-based radar. So this is from a distance of 380,000 kilometers. And what you can see, this is the cross-track direction here. And you can see the fringes going very, very fast. And even through the bottom of craters that should be relatively flat, you can see the fringes changing very, very, very quickly. But here's what happens after we do the flattening. So if I remove the flattening, or if I remove the curved shape of the moon, then you can see now the phase looks very flat over the bottom of the crater, and we can see the fringes changing as I walk up the top of the crater. So in this scene here, there's actually a lot of topography. There's over 12 kilometers of topography in this small area of the moon, which is about 600 kilometers by 300 kilometers. How many tell me how much topography variation there is on the Earth's surface, excluding the bathysphere for the moment, so it's land surface, how much topography variation? How high is Everest? Somebody doesn't know.
1848.
About 8,800 meters, if I remember correctly, on that order. So there's more topographic variation in this small area of the moon than there is over the total land surface of the Earth, just to give you an idea of what's going on. If you throw in bathymetry, it's 18 kilometers or thereafter for the Marianas Trench, which is the deepest part of the ocean, actually Challenger Deep. Okay, so then these fringes that I was showing you earlier, these have been flattened because they obviously follow the local slopes. So these fringes here have been flattened, so these don't represent the natural fringes that were required by the rate. And then I will skip this. Wonderful formulas, but don't have time for them. Now, how much does the phase change as a function of height, terrain height? Not range now, but range as a function of height. But we have this formula for the range, phase as a function of range. So if we know how range changes with height, then we can work out that formula. And I've done it here for you. And again, what we see is the change of phase with respect to topographic height depends upon the perpendicular baseline length. So again, you get more fringes or a bigger perpendicular baseline, and it's inversely proportional to the wavelength and to the range. So if I want a very sensitive interferometric mapping system, do I want a small or short perpendicular baseline? Large or small? Take up the limit again. What happens in the limit as B per goes to 0? What do you get for the phase? What?
You want smaller baselines.
You want smaller baselines. How many people vote for smaller baselines? 1, 2, 3. How many people want longer ones? How many people don't have a clue? Like that's it. Well, let's look again. Change of phase with respect to height. If the perpendicular baseline is equal to 0, what is the change in phase with respect to height?
0.
Zero. That means no matter how you change the height, how much change in phase are you going to get? Zero. So it means how much information are you getting about the topography? Zero. So do you want a small baseline? No, you do not. You need a bigger baseline if you're going to get sensitivity to the topography. So I'm saying take a look at the limits to help you figure out what sensitivities are important or not. So bigger baselines lead to the more sensitivity, but they also lead to faster fringe rates and they lead to more difficulty unwrapping. So again, to design a topographic mapping system, there's going to be a balance between the sensitivity you want to get the topographic accuracy you need versus the ability to actually unwrap the phase and be able to solve for the heights themselves. One metric that people often use to determine as a metric of the sensitivity of a height mapping system is the so-called ambiguity height, which is the amount of phase change or 2 pi change in elevation. So basically, you take the reciprocal of this and then multiply times 2 pi, and that will give you this formula here. That's the ambiguity height. So the smaller the ambiguity height, the more sensitive the system is. So if I have an ambiguity height of 300 meters, like for SRTM, then that turns out to be, between 150 and 300 meters is what it was. It varied across the swath. That's a problem that leads to an unwrapping problem that was solvable, but reasonable height accuracies. If I have an ambiguity height of 10 meters, that's going to be really tough to unwrap around the world unless, and so I'm going to have really good sensitivity over flat areas. I'm going to get really good height mapping accuracy, but I might have trouble in really mountainous regions like in the Andes or in the Himalayas, which have very steep slopes. So again, to have a good topographic mapping system, you're going to want something that's, a balance between the two things. I won't go into this in any detail. I'm just going to state verbally what these formulas tell you. This is the sensitivity of the height to the baseline length error and baseline angle error. And I'm just going to make 2 points about it. One is these formulas, trust me, say that they're very, very sensitive. But there's a big difference between these two in the following sense. Notice that the sensitivity of the height to the baseline length error depends upon the baseline length. So I can affect this sensitivity or how sensitive I am by changing what the baseline length is. So I have a choice when I'm designing my system to help make things better. This formula here for the orientation angle of the baseline, how well I know it, how tilted it is, only depends upon the range and the look angle. So the only thing I could do to make this better is fly closer. That's my only choice here. So the further away I am, the more accurate my angle measurement has to be. And for some systems, if you're in a spaceborne system, rho is very large, which means you have to know that angle very, very, very well. So. Another thing about interferometric mapping systems that I wanted to point out is people often ask, well, what height am I actually measuring? And that's a very good question. And it depends on what you're looking at and what wavelength you're using. So here's interferometric mapping that was done using 3 wavelengths, C, L, P, and X. And then there was a LiDAR that measured the top and the bottom of the canopy, which is the green line and the black line here that you see. So the interferometric height that you measure actually depends upon the volume you're scattering from. So different wavelengths penetrate differently, as we learned before. And so where you measure in a canopy, for instance, this is over a vegetated terrain, depends on the wavelength I'm looking at. So X band and C band measure toward the middle of the canopy, and P band, a very long wavelength, measures near the bottom surface. It penetrates all the way through the vegetation, or can penetrate all the way through the vegetation. So when you're looking at a height map, like from SRTM or Tandem X, we often call that height the reflective surface elevation. And its elevation is going to depend upon what it's scattering off of. Is it looking at ice? Is it looking at trees? Or is it looking at a bare surface? So you may ask, well, is there a way to correct for this? And there are techniques that can try to correct for this. One is using the interferometric correlation, which is shown down here as a way to try to get a correction for this. I'll try to talk about the correlation a little bit in the very closing minutes of the lecture. But another technique is to combine polarimetry and interferometry together. So if you have a polarimetric interferometric system with the right wavelength, you can actually figure out where the top and bottom of the trees are and then get a way to correct the data. So there are a number of different ways to try to approach the problem. But remember, when you're looking at data, you need to try to understand, make sure you understand what it is measuring. So people use SRTM data and they use it as a reference for the Earth's topography. It is a very good one, but it's a reflective surface thing. So we know that it's going to follow the trees or whatever vegetation that it's done in the season that it was collecting it, which happened to be in the winter in the Northern Hemisphere. So, and these things can change seasonally where you're scattering in the canopy. So you may get a different answer in the summer and the winter if you go and measure it. This is an example again of penetration at different frequencies, and this is L, C, and X band minus the P band, which is penetrating to the bottom. And you can see that you see the tree heights getting progressively smaller as you're getting to longer and longer wavelengths because you're seeing different penetrations into the canopy. All right, so that's the quick introduction to topography. And so now I want to do a little bit about deformation. So what we know radars are good at is measuring distance. So if I fly by one time and I'm looking at a volcano, I can measure the distance to a point on its surface. Then let's suppose that my volcano inflates at a particular point on the surface. So you can see, there it goes, it inflated. And then I fly by again. And now, if I fly my plane by in exactly the same path I did the first time, and now measure the distance here to the point on the volcano, the difference is going to be different. So I'm going to have D2 and D1. And what is interferometry good at? It's good at measuring the difference in distances. Now, if the atmosphere changes, then I will also measure the difference in the atmosphere. So the phase is going to be the surface deformation, which is the desired signal. If the baseline is not zero, if I didn't fly my path exactly the same as I did before, which is nearly impossible to do, I'll get a signature that's due to the topography. And then I'll be also sensitive to the change in the atmosphere between the observations, between the two. So that's typically what my deformation signature is. It's comprised of something I want, as usual, and things that I don't want. Now, fortunately, this signal, if I have a good DEM, I can take care of this. I can remove this. So now that we have really good accurate maps of the world, like from SRTM or TandemX, et cetera, we have really good topography for most of the Earth, so we can remove this pretty well these days. When I started out in this game a long time ago, this was a really big source of a problem for us. Now, not so much. And then the atmosphere, though, is still there. There's been a lot of improvements in how to deal with this. You can exclude that for Venus. It turns out water vapor is not a problem at Venus, but sulfur dioxide is a problem for Venus. So this is what the fringes look like for an earthquake. This is an example. It's here in Southern California. And basically, the surface will cause a change along the line of sight. So the deformation that you're measuring with the radar is the component along the line of sight. So even though there may be certain horizontal motion, vertical motion, and a long track motion, what the radar sees is the projection of the total motion onto the line of sight. So if the motion is perpendicular to the line of sight, I'm not sensitive to that at all. So the surface may be moving a lot and I won't even notice that. And the vertical and horizontal components will couple together into my phase measurement. So I'll see a combination of the two of them. So it's not all vertical or not all horizontal if the surface is moving in both directions simultaneously. So now that I have so many smart people in the room that are still awake, sort of, suppose I wanted to know what both components of the, suppose I wanted to know what the full vector motion was. What could I do? I can't hear whoever's saying.
We can decompose the vectors to x and y.
You need two interferograms from two different.
Exactly. So make maps from two different directions so I get different projections. So what you need to do, if you want to know three components, how many different directions do you have to have? Three. If you want to solve for three unknowns, you need three observables. Now, you can't, the angular separation has to be right. Otherwise, if you try the same path 3 times, that doesn't help you very much. So there has to be the right geometry of the repeat passes. But in principle, I can solve for the full vector deformation, which we've done with both spaceborne to a lesser extent and the airborne systems. You can solve for that. So right now, oftentimes people have to use models to try to use just the projection in one direction. But there's with more and more sensors being out there, with more and more diversity, people are working more and more on getting vector full or at least more components, 2 or more components of the motion from the differential interferometry. So the 2 observations are going to be done there. You're also going to get a noise component, of course, as well as the deformation, the projection onto the deformation onto the line of sight that you're getting with the system. So, as I mentioned before, for repeat pass interferometry, it turns out that you need a couple of conditions to be true. One is something called the critical baseline. The separation between the points has to be less than the perpendicular baseline has to be less than a certain distance. You probably won't have time to get to the formula in this paper, but the biggest perpendicular baseline you can live with is the critical baseline. And so not all geometries work. And so that's why you need to control the repeat pass geometry. And typically, if you're doing repeat pass interferometry, you want to make that as small as possible. You want to be a small fraction of the critical baseline. The other thing is that you have to get the pointing direction to be the same in azimuth. So, and in order to do, and that can be difficult for an airborne platform, but that's why we use the electronic steering for UAV SAR, so we can force that to happen. Let's see. So as I mentioned, you get the topography term, which is the projection of the baseline onto the line of sight, and the thing that you're sensitive to is the projection of the deformation onto the line of sight. And then if the topography is known, then I can correct for this term. And there are a couple different ways of doing that, which I won't go into because we don't have the complete time. I will make a quick note. One needs to be really careful about the sign convention. And unfortunately, there's 4 possibilities floating around. It's the convention that people use for the interferometric phase, the convention that people use for the interferogram. And depending on what they do will determine what the sign means on them. So you have to be careful to know what conventions are used to track through. Am I inflating or deflating? And you really don't want to make the wrong conclusion, and this particularly in your thesis. So be careful to follow through the phase conventions for the data that you're using, because it makes a difference in how you interpret the data. So one of the major developments in repeat pass observations these days is time series, with things like Sentinel-1 that collect, people who've used hundreds of interferograms over a site. This allows people to solve for topographic error and atmospheric errors in a very robust way. So these dense time series have been a big game changer over the last decade and a half or 2 decades, and have really changed the state of our understanding for a lot of deformation. So people have been able to, and gone and done a lot of very systematic mapping for many places in the world, trying to understand the amount of deformation. Here this is looking at it again from 2 different directions to try to get a better idea of the vector deformation that is going on. Why do we care? Well, as I mentioned before, the deformation of the fringe pattern that you see is an indication of what's going on at depth. And so people use models, geophysical models. This is a case where there was a model for the amount of seismic rebound that depended upon the amount of basically embedded water in a given area, so plastic elastic theory. And so using models, you can get better agreement to try to understand the fringe pattern and understand what's happening at depth. So coupled with models, is like an X-ray of the deep lithosphere on the Earth to figure out what's happening on the surface. So, you have your error terms. You have your interferometric phase error. You have your DEM error for removing the topography. Your atmospheric error from whatever models that are floating around in the data for what component of the troposphere you're not able to remove. And you have baseline errors. So all of those can contribute to your understanding of what the deformation source that you're getting. So you need to understand and bound the errors to understand the total error in your observation that you're making. And again, the most dominant source of errors these days are phase noise coming from temporal decorrelation and atmospheric error. Skip this. You can use airborne and spaceborne data for doing repeat pass interferometry. For a long time, only spaceborne data was used for this because the flight path problem was really caused so much error that you couldn't really do repeat pass too well. You couldn't reconstruct the baselines well enough. But spaceborne, again, your revisit times are limited by the laws of orbital mechanics, or you need to have constellations of multiple satellites to get the repeat orbits down. This is now 5 to 45 days, depending upon the type of system. The airborne system, we've often made repeat pass measurements over glaciers of 20 minutes, so we can get very short repeat times to look at very fast-moving glaciers, for instance, with airborne systems. The mapping scale, people are now looking at making, with ISAR, global deformation maps, wall-to-wall coverage of the Earth with a deformation map. Airborne, you're limited again to regional mapping. Again, the accessibility problem, spaceborne everywhere, spaceborne wherever you can get permission to fly. Baseline estimation, much easier for the spaceborne case. Much more difficult in the airborne case. Atmosphere is the same for both guys, same as before. No ease one way or the other. But spaceborne has another problem. There's another layer to the atmosphere called the ionosphere. And the ionosphere can be a big problem. And the longer the wavelength, the bigger the problem. So where you want to have long wavelengths to avoid temporal decorrelation, then this guy comes into play to be a source of error. Again, nothing's for free. So L-band and P-band are particularly affected by the ionosphere. But airborne systems are flying well below the height of the ionosphere, so they do not have to worry about the ionosphere at all. So they both worry about tropospheric water vapor. Only spaceborne systems have to worry about the ionosphere. And in my last 5 minutes, I'm going to say a little bit about the correlation, and I won't have a chance to really go into the theory in any detail. So the interferometric correlation is another observable that comes with interferometric data. On the last 15 minutes, sorry, for the quiz. The interferometric correlation is a measure of how alike the signal is between the two antennas that are receiving the data. And it's a number between 0 and 1. So 0 means the signals are not alike at all, and 1 means they're identical to each other. And the value of the correlation, denoted by gamma here, is it can be related to the amount of interferometric phase noise. So the interferometric phase noise, this is an approximate formula, again, with an equal sign in front of it, which is related. This is the Kramer-Rao bound, in case somebody really wants to know. And it says that the interferometric correlation is related to the number of looks, which we learned about before, how much spatial averaging we take in our interferogram, and the interferometric correlation. So what do we see? If the interferometric correlation is 1, the phase noise is what? Correlation of 1, gamma equals 1 means 0, no phase noise, which means we have really good data. And if the correlation is 0, bad thing happens. So, and again, that's why this is an approximate formula, not exact. Obviously, there's a problem there at 0. So, but what is true, and I'll show a plot in just a second, is the worse the correlation gets, the worse the phase noise is. So, if you're trying to improve the correlation, the interferometric phase, you either find some way to help improve the correlation or you increase the number of looks. That's what you have to do in order to get your phase noise down and improve your either topographic measurement or deformation measurement, depending on what you're trying to do. Now, there are different types of decorrelation. So thermal noise is called SNR correlation, and there's a formula for that. So we can actually predict very well what the SNR correlation is, knowing the SNR. Different advantages. So the fact that we have a baseline leads to a change in the signal. And it better because obviously if there was no change in the signal, then there's no information there. There's no topography, there's no deformation. We do want a baseline of 0. But whenever we have a non-zero baseline, we get geometric correlation. And there's a formula for that too, in terms of the perpendicular baseline length. So we can know what that is. Volumetric correlation. This is a difficult guy. This is saying, suppose we have a vertical arrangement of scatters, like a tree or a building, inside a resolution element, a pixel. Then the fact that I have a vertical arrangement of scatters will also cause some decorrelation. So bad news is it causes some decorrelation. The good news is there's a signal there that can be exploited to figure out something about the distribution of scatters in the vertical direction. And that's how polarimetric interferometry works. It exploits the volumetric correlation to figure out something about the height of the tree or the thickness of the ice that you're imaging. So this is not only diagnostic of the phase, it's a signal unto itself that can yield valuable geophysical information. I'm not going to talk about rotational decorrelation. The last type of decorrelation is temporal decorrelation, and that's related to the changes in the pixel between observation time. So if there's a lot of change, the correlation can be nearly 0. For instance, over water completely decorrelates very quickly, so water observations over the ocean, they always decorrelate. Now, the bad news about the temporal decorrelation, as you might expect, there is no formula that works everywhere for all types of surfaces. There are models that are good heuristic models that give you an idea of what may be happening, but there's no predictive model that'll say, when this happens, you have this much amount of temporal decorrelation. Yes.
So for the volumetric correlation, how good is that working for the urban areas also? Would we have like a factor?
Well, there's no factor, but you will get volumetric decorrelation in an urban area. It can be related to what's in the scene. It's complicated. This is the underlying story. All right. So the good news about the total correlation that you get is it has a very simple relationship to the various components. It's the product of the individual components. That's not exactly true, but for today it is exactly true. So if any one of these guys is bad, the total correlation is bad. So this is a thing where everybody goes along with the worst playing guy in the field. So if you have a bad baseline decorrelation, bad volumetric decorrelation, or temporal decorrelation, you're going to have bad correlation. So these two signals, the volumetric and the temporal, can be signals useful into their own right for geophysical information. So as I mentioned, the volumetric correlation can be used to estimate the height of the volume, like I'll say a tree or forest height. Temporal decorrelation has been used to make diamond proxy maps. So for instance, after an earthquake, people look at the temporal decorrelation and look at the pixels that have a lot of, and they make estimates of how much damage there is in an area. And this has been used very successfully and operationally to understand, the amount of damage that's happened after an earthquake. You can use this to get an idea of, where there's a lot of changes in the surface or vegetation. There was a really cool image made a long time ago where somebody had taken an image and then they had somebody walk across the desert and then they showed their footprints made in temporal decorrelation as they walked across, so they were able to see differences there. I had a friend at work who was looking at one of the Nazca sites. People know about those. Those are the images that the Incas made from rocks of various geometric figures there. And they measured some disturbances that somebody went out and disturbed one of these things, which is unbelievable, but they did. And they were able to see that in the temporal decorrelation. So there's another, again, it's a type of damage map. So these signals are, in addition to being diagnostic to the amount of phase noise, provide additional geophysical information about what's going on, sometimes to a very quantitative extent and sometimes to a qualitative extent. But it's one of the other parameters that one wants to look at when trying to understand the data. So when you're first starting to look at data and looking at the phase, you want to look at the fringes, but you also want to look at the correlation, which will give you an idea of what the quality is in the data that you're looking at. So there's a number of happy formulas there for certain types of it, but I wanted to point one other thing about the phase estimation and correlation. So the people have to estimate the correlation from the data. And so there's a formula for estimating it based on the data. It's in here, but I'm not going to go through it. But the point I want to make about the correlation estimate is what's called a biased estimate. And what that means is that the lower the correlation is, that when you make an estimate of the correlation using that formula, it can appear higher than it really is. So the correlation is always biased to the high side. And so it depends upon, and how biased it is depends upon the level of the correlation and the number of looks that you use. So here's an example where there's true correlation is 0.9, and I used 49 looks to estimate the correlation. And I see something that's centered just a little bit more than 0.9. But if I only use 9 looks to estimate the correlation with a correlation of 0.9, I see something that's up around 0.95. So I have a bias in what my correlation was. So I think it's higher than it truly was. And to show how bad it can be, if the correlation were truly 0 and I use 49 looks to do it, I would estimate a correlation of 0.1. So when you're estimating and you're using tools to estimate the correlation, you want to know how many looks were used, because there will be a bias to it. Now, sometimes people try to remove that bias from the correlation estimator, and you have to be careful because then you can get negative correlations when you make that correction. But you need to be aware that correlations will tend to be biased high. And the lower the correlation, the higher the bias will be. And let's see. Is there anything else I really want to say? As maybe one last thing about volumetric correlation. So I will say a little bit about this complicated formula and then show a simple example and make a point from that simple example, just as a final note for people who are interested in estimating, say, tree height from the data. There's a formula for the volumetric correlation, and it's related to how much scattering, gamma sub z means how much energy is scattering as a function of height within the volume. And this k sub z is related to the baseline length, the perpendicular baseline. So it's the derivative of phase with respect to height. This formula here, for those who know this formula and for those who don't, it doesn't matter. That's a Fourier transform, by the way. So the volumetric correlation is related to the Fourier transform of the vertical scatter in the volume, and where the Fourier factor depends upon the baseline length. So if you know what gamma sub z is, then you can actually compute this Fourier transform, and you can compute a formula for this in certain cases, simple cases. This is the example of L-band volume correlation. So you can see the different baselines here. As the lengths get larger, you get more and more volumetric correlation. For zero baseline length, there is no volumetric correlation. So this is an amplitude image. So you can see the forest here shown is in the various grayscales, the black area or open areas. So you see that the volumetric correlation gets much smaller in the open areas and is higher or is lower in the treed areas, and then it's higher in the flatter areas. So, and then that becomes more and more pronounced as the baseline length gets longer. So you get more and more information from the volumetric correlation as the length gets larger. Then I'm going to do one other thing. I'm going to do one simple model. Suppose you have a volume that consists of only 2 points, a top and a bottom point, and that the amount of scattering that you get can be different, A sub t from the top and A sub b from the bottom. And so I'll call the ratio of that A sub b over A sub t r, and the height difference between them delta h. And you can write down a formula, in that case for the volumetric correlation, by computing that Fourier transform, and you get a formula like that, which is all fine and good. But what does that mean? So what happens is, this is an example of the ratio of the top to bottom power, and this is the volumetric correlation for separation of 30 meters for these two for 60 meter baseline length. And what you see is when the correlation is balanced between the top and the bottom, that's when you get the maximum amount of volumetric decorrelation. Why is that? Well, let's suppose that all the scattering was coming from the top and I was getting nothing from the bottom. Well, then that would be like I wasn't seeing the volume at all, right? I mean, just because it's a single point, doesn't see anything about it. So then the correlation goes to 1. There is no volumetric decorrelation. And similarly, if I'm seeing everything from the bottom, it still looks like a single surface, doesn't know anything about the top part. So the correlation goes to 1 again. So when is it going to be the maximum? It's basically when it's balanced between the two. So I'm going to see things as if they were coming from the middle over the total volume. So then you see that. And if I'm going to estimate the tree height, what you can see is the height that I would measure, the interferometric height that I would measure, and I'm going to see at the very top when I'm scattering, when I'm getting powers mostly coming from the top. As I get balance of power, I'm going to get a height in the middle, 15 meters, makes sense. That's what you sort of expect. And as I go from the bottom, I'll get a height of 0. So your interferometric height, and this is what I was telling you before, like where I'm going to measure the canopy, depends on how much power is distributed at various parts within canopy. Now, suppose I wanted to invert my volumetric correlation for a height with this very simple model. Well, this very simple model already shows you something very interesting. So it turns out here's a formula for the height involving the interferometric correlation. So there's the volumetric correlation there. There's the K sub z, which depends upon the baseline. But notice there's one other parameter in the formula, R. That's the relative how much power I'm scattering from the top and the bottom. And this is the issue with all these sorts of volumetric inversion algorithms. They end up requiring you to understand something about the scattering in order to be able to estimate the canopy height. So I can measure the volumetric correlation, that's all fine and good, but I'm going to need to be able to estimate some other important information somehow from the data in order to be able to get to an actual volume height. And that's where polarimetry can come into play. By measuring the volumetric correlation and how it differs for different polarizations, basically allows you to learn something about the scattering and then invert for the height, again, under some sort of simplifying assumptions. So the point is that these parameters, the correlation can be very, very useful for estimating things, but usually I have to make some sort of assumption and I need some additional information in order to be able to use it. There is a model that doesn't depend upon R, assuming uniform scattering, and then you can just make an estimate depending on that. But that model is good under some cases, but it's not, uniform scattering doesn't represent the real world. And so it's only good some of the time. And so you want things that are more robust, that work more universally. And I think at that point, we've finally reached the end of my lecture time. Hard to believe, but we are here. before I give out the quiz, I guess I don't even have it, so before somebody comes back to you guys, you have the quiz. Are there any questions before we do this? If you don't want the credits, you don't have to take the quiz, so you gain yourself a half an hour. For those of you who do want the credits, you can take the quiz. I hope that you were able to get something useful out of the class. I realized that this was a ton of information in a very short period of time, and I don't expect anybody to have possibly understood everything in one day. It's just not possible. I hope if you get the notes and you get them downloaded, they'll be helpful. I try to provide details in them for those of you that want to get more detail. And there are a lot of other resources out there for learning more about interferometry, but I hope at least that you learn how valuable it is and what the useful information that you can get out of it, and some of the sensitivities. And I thank you very much for attending the lecture throughout the day.